Welcome. Our topic today is radioactive decay. You probably have heard of radioactive decay before, and probably it brings to mind things like superheroes, mutant ninja turtles, or three-eyed fish. But what is decay really, and what do we know about it? Our goal today is to look at what happens to the nucleus of an atom when radioactive decay occurs. To understand what we know about radioactive decay, let's start at the very beginning. Henry Becquerel was the first person to notice that substances like this uranium gave off energy all on their own, as recorded here on these photographic plates. He was soon joined in researching this amazing phenomena by Ernest Rutherford and Pierre and Marie Curie. Henry, Marie, and Pierre won the Nobel Prize for Physics in 1903 for their groundbreaking work on radioactivity. This made Marie Curie the first woman to ever win a Nobel Prize. As these scientists discovered and tested radioactive elements, they found out that not all radiation was the same. For example, some radiation could be blocked by a simple sheet of paper. Other elements gave off radiation that could pass easily through paper but could be blocked by aluminum. And still other elements gave off radiation that could easily pass through paper, aluminum, and could only be blocked by heavy layers of lead or concrete. Based on this level of penetration, or penetrating power as they called it, they named the elements after the first three letters of the Greek alphabet: alpha radiation, beta radiation, and gamma radiation. They found that radiation differed in other ways as well. In the apparatus shown here, a radioactive sample would be placed inside the lead block to the left. The lead block had a hole carved in it such that the exiting radiation would be funneled into one column that would then pass through either an electric field or a magnetic field. If they placed a sample that emitted alpha radiation into this contraption, they found that all of the alpha particles would be bent in one particular direction, towards the negatively charged electric plate. This meant that alpha particles must have a positive charge. When they placed a sample that emitted beta radiation into the same apparatus, they found that these particles would bend in the opposite direction, meaning that beta particles must have a negative charge. And when they placed a sample emitting gamma radiation into the detector, they found that these particles would travel straight forward without bending in either direction, meaning that gamma radiation has no electrical charge. So, what's actually happening when something decays radioactively? We know that within the nucleus of an atom, the electromagnetic force is pushing all of the positively charged protons apart, and that the strong force is pulling the nucleus back together. In a stable isotope, these forces roughly balance one another out. The graph shown here depicts stable isotopes. On the horizontal axis, we have plotted the number of protons in a nucleus, and on the vertical axis, the number of neutrons. If you have equal number of protons and neutrons within the nucleus of an atom, we say you have a 1-to-1 proton-neutron ratio. That's shown with this red line. Notice that most of the stable isotopes, the blue dots, are not on the red line. They follow a steeper path, meaning that they have more neutrons than protons. This makes sense if you think about what happens as you add particles to a nucleus. Adding a proton increases the electromagnetic forces pulling it apart, whereas adding a neutron does not. So, as you build bigger and bigger atoms to keep them stable, you need more neutrons than protons. But even then, you end up with some unstable isotopes. In the process of radioactive decay, elements move from an unstable to a stable state. We will talk about 4 specific types of radioactive decay. But before we get into those particulars, let's talk about what's true about all nuclear reactions. We'll use the example below. Here we have potassium, K, decaying into calcium, Ca. The other terms in this equation might not look familiar. The first one, 0, -1e, represents an electron. Remember that the top number, the 0, is the nucleon number for a particular isotope. Since an electron is not a nucleon, we write a 0 there to represent that it does not contain nucleons. The bottom number is usually referred to as the atomic number and represents the number of protons. But in a nuclear reaction, this can also be thought of as the charge on a particular element. This -1 denotes that an electron has a charge of -1. The other unfamiliar term in this equation is probably this Greek letter nu. It stands for a neutrino, and the line over the top indicates that this is actually an antineutrino. More on those later. One of the key ideas within physics is that there are quantities that are conserved. So what's conserved in a nuclear reaction? Clearly, the number of individual elements is not conserved, as here we have potassium turning into calcium. What is conserved is the number of nucleons. The potassium, 40, on the left-hand side, starts off with 19 protons and 21 neutrons for a total of 40 nucleons. It decays into calcium, which has 20 neutrons and 20 protons, also for a total of 40 nucleons. The electron and the neutrino contain no nucleons. The other thing that is conserved that will be important to us is the charge. The potassium starts off with 19 protons, meaning that it has a charge of positive 19. It decays into calcium 20, which has 20 protons for a charge of positive 20. But it also creates an electron that has a charge of -1. Together, the 20 and the -1 give us a total charge of 19 on the right-hand side of the equation as well. Nuclear reactions also conserve momentum and mass energy. The conservation of momentum is actually how we know that the neutrino exists at all. We will talk more about the conservation of mass energy when we look at fission and fusion. Our first type of decay is alpha decay. In alpha decay, a large nucleus simply loses 2 protons and 2 neutrons. We call this the alpha particle and would write it this way, 4,2 alpha. Notice that an element with 2 protons is helium. That means that an alpha particle is really just a helium nucleus. An example of an element that undergoes alpha decay is uranium-238. This isotope has 92 protons and 146 neutrons. In the process of alpha decay, 2 protons and 2 neutrons escape as the alpha particle, and we are left with a nucleus with 90 protons and 144 neutrons. Element 90 is thorium. Therefore, we are left with thorium-234. This is an example of transmutation, when one element radioactively decays and becomes a different element. The next type of decay is beta decay. There are actually 2 varieties of beta decay, beta minus and beta plus. Beta minus is called minus because it emits a negatively charged particle. Beta decay is slightly stranger than alpha decay, because in beta decay, either a proton turns into a neutron or a neutron turns into a proton. In beta minus decay, a neutron becomes a proton. It emits a beta minus particle, which turns out to just be an electron. We will sometimes in a nuclear equation write an electron this way, 0 because it is not a nucleon, and -1 because the number of protons can also be thought of as the charge number. Beta minus decay also emits another tiny particle called an antineutrino. An example of a particle that undergoes beta minus decay is carbon-14. Carbon-14 has 6 protons and 8 neutrons. As it undergoes beta minus decay, one of those neutrons turns into a proton, leaving it with 7 protons and 7 neutrons. This element has also undergone transmutation because it is no longer carbon, but element 7, nitrogen. We complete our nuclear reaction equation by adding our electron and our neutrino to the equation. In many ways, beta plus decay is the opposite of beta minus decay. In beta plus decay, a proton becomes a neutron. And the particle that's emitted as the radiation particle has a positive charge instead of a negative charge. The beta plus particle is called a positron. It is actually the antimatter equivalent to an electron or an anti-electron. The symbol for a positron is 0 plus 1. In every way, it is like an electron, except for that it has the opposite charge and the opposite spin. This reaction also emits a small neutrino. An example of an element that undergoes beta plus decay is sodium-22. This contains 11 protons and 11 neutrons. As it undergoes beta plus decay, one of the protons turns into a neutron, leaving us with element 10, neon. Notice that it still has 22 nucleons, but now only 10 protons. To complete our nuclear reaction equation, we will write the symbol for our positron, E plus 1, and our neutrino. The last type of radioactive decay is gamma decay. This is slightly simpler than the other forms since there is no transmutation. In gamma decay, a nucleus simply has some excess energy. We say that it is in an excited state. In order to release that excess energy, the nucleus emits a gamma particle, which is simply a photon or a particle of light. This particle of light is in the gamma range of the electromagnetic spectrum. An example of this type of decay is polonium-210. We write the asterisks next to the PO of polonium to indicate that this nucleus is in an excited state. As it undergoes gamma radiation, or gamma decay, it becomes a regular nucleus of polonium-210. Notice that the nucleon number and the charge number are exactly the same. To complete our equation, we simply write plus gamma to indicate that a gamma particle was released. Another way to think about these decay reactions is to plot them on the periodic table. Alpha decay causes an element to lose 2 protons and 2 neutrons. In our example, we saw uranium decaying into thorium, moving from element 92 2 spaces to the left to element 90. Beta minus decay causes an element to lose 1 neutron and gain 1 proton. We saw carbon decaying into nitrogen and moving 1 space to the right on the periodic table. Beta plus decay is the opposite, where an element loses a proton and gains a neutron. This would cause an element to move to the left 1 space on the periodic table, for example, moving from carbon to boron. Gamma decay does not cause transmutation. Therefore, an element undergoing gamma decay doesn't change places on the periodic table. Decay reactions do not happen in isolation. In fact, quite often, more than one reaction must happen to move an element from unstable to stable. Consider the case of lead-210. Lead-210 is an unstable isotope of lead. It undergoes beta minus decay, turning it into bismuth-210. Bismuth-210 is also unstable, and it undergoes beta minus decay, turning it into polonium-210. Polonium-210 is also unstable, and polonium-210 undergoes alpha decay, turning it back into lead. But this time, it turns it into lead-206, which is a stable isotope of lead. This is an example of a decay chain, moving one unstable isotope to a new stable isotope through several decay reactions. Nuclear physics is a fascinating topic. Hopefully, this has helped to clear up some of the mystery surrounding radioactive decay. I hope you enjoyed, and as always, happy physicsing.